Okay, so this lecture we will talk about line integral, and this will be a short one, and we will give the definition and show some basic examples, and leave the heavy computation to next lecture. So we have line integral, and let's recall. So for the category A, so far we have considered the following integrals. So in 1D, we consider some integration over an interval a to b. So the same another notation is some domain in 1D. And in 2D, we consider the double integral over some domain in 2D. So R is a domain in 2D. And in 3D, we have triple integral over some solid. So V is a domain in 3D. Okay. And in the following, in this chapter, we will consider some generalization. So we will be interested in the following cases. So first, I just write down like this. So C is a curve in 2D or 3D. So if we draw a picture, suppose we are in 3D, X, Y, Z, and you have curve, and we are interested in some kind of integrals along this curve. This is reasonable because suppose you are Ant-Man live on a string, you cannot see the behavior outside the string, so you are one-dimensional. But actually, the ambient space is three-dimensional. So even if you are Ant-Man, you want to calculate, you want to do some calculus. So the problem just like you want to do calculus on the line, and it's not far from our true universe. So our universe is a 3 plus 1D space, but we don't know if this space is a subspace or some bigger space. So we just do everything within this subspace. So the keyword is we want to do calculus in subspaces. So this is one example. But of course, here we need to make sense of what is ds, right? And we will give two methods to define line integrals with respect to two different problems. So we will leave this later, what does this exactly mean. But basically, we want to do calculus. We want to integrate some integrals along this curve C. Okay, a little bit more general, we can consider a surface in 3D. Suppose you have a surface in 3D, right? And you want to do calculus on surface. So here, S is a surface in 3D. We want to do calculus in this surface. So here, the same question, we need to make sense of dA. Otherwise, you cannot do this integral. So to be more precise, why we need to make sense of it? Because in A category, when you speak of, for example, for the line, you speak of f dx. So dx is well defined. because you have interval a, b. X is the only variable you have at this moment. And if you are doing double integral, what's the notation here in R, on R? Then dA is dx dy, and x, y are variables of R. And similarly for V, if you have dv is dx dy dz. That's the only choice you have because x, y, z are all the variables of V. Here we use the fact the integral is on the whole space. Therefore, you don't need to choose dx, dy, dz. It's automatically given. But when you do calculus on subspace in B category, you might have trouble because suppose you have C in R2, then of course for C, C is one-dimensional. Okay, so you only allow one variable to parameterize it. So when you do integration, it's a one-dimensional integration. But R2 has two variables, x, y, and for the differential, you have dx, dy. So which one should be ds? That's a subtle question, and we will answer. The quick answer is none of them are, but some combination of them will be the ds here. And similarly for dA here, S here, so S in R3, then the problem is R3 you have dx, dy, dz, three independent differentials, but S only has two free variables. It's two-dimensional. So dx, dy, dx, dz, dy, dz, which one should correspond to dA? So the quick answer is certain combination of them will be dA. Okay, so we know the first step, if we want to do calculus on subspace, we need to make sense of the integration differential ds, dA here. So it turns out whenever you have problem in mathematics, especially for the definition one, you turn back to physics or geometry for some intuition. And in physics, it's very natural. You have two choices. So we talk about the first one. So it's called first kind line integral. Okay, so before that, I should say we will talk about line integrals. Okay, and the first kind line integral. So this is related to the following. Suppose we are in 2D xy, and you have a curve, and let's set up something. X is xt, y is yt. This is parameterization. And now, which what kind of geometric quantity can you associate with this curve C? So we already know that the arc length is a geometric quantity. Attached to C. And so this is from geometric side, geometry. And from physics, what do you have? You might ask, what is the density? Sorry, what is, for example, total mass? Yeah, I know now you are mad. You are mad at me whenever we talk about total mass or the center of the mass. So total mass, let's recall, it's basically if you think of this as a string. If the string is flat, is straight, then it's just the integration over some interval of the density function. Okay, so basically it's a integration over the length, so, I should say some kind of length, d length, and C, kind of like this. You have a rough idea, but it's not that convenient to represent in this form. So we think what's our usual way to do it for 1D integral? We are able to do it on line. So how to turn this back to a line? So we use parametrization. Suppose this is T, and starting from A, B, so this is your A, this is your B, for example. So use this to parametrize it. So what does parametrize mean? For example, this parametrization maps this interval AB, blue one, to the red one. And in particular, if you have a sequence of points here, for example, let me call A1, A2, A3, A4, blah, 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 blah. And then you have corresponding image of A1, A2, A3, A4, blah, 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 here. Okay, and now suppose you have density function f. You want to integrate this one, so you can pull back your f. Suppose you have function f xy here. Then you can pull back the function to be f xt yt, right? Because for each point t here, the corresponding point here is xt yt. So the function value of f at this point is fxtyt. And then the integral infinitesimally on this side. So on the right side, so the integral f ds is not well defined yet, but we have the geometrical intuition. There should be summation. You cut this into small pieces, I, and the small interval like this. So between ai plus 1, so it's curved it's a small curve, and do some I should say like this, is do some integration on this small curve ai to ai plus 1, and f ds kind of. Okay, then approximately equals to you approximate small curve by intervals, then what do you have? We can represent as Riemann sum. So f, so you choose some point xi, yi star, delta si. So delta si, we can write one more step. Delta si just length of the interval from ai to ai plus 1, and recall the formula for recall. Suppose you have interval. So suppose this is x t, so x, okay, ai, y ai, here x ai plus 1, y ai plus 1. So what is arc length? So this approximately equals to delta x, I should say equals xai plus 1 minus xai. So approximately this approximately equals x prime t at ai and delta ai. Similarly, for y, you have y prime ai times delta ai. And then the length, just a square root a minus xai square plus yai plus 1 minus yai square. And then if you plug in this, the above two formula, this approximately equals to x prime square plus y prime square delta ai. Okay, then you put this back here. So what you have is you will have x prime ai square plus y prime ai square square root and the delta ai. Okay, then if you view this as a function of t, so because ai just nodes for the interval in the t-axis. Okay, so this will approximate equals to integration f x t y t square root dx dt square plus dy dt square dt. Okay, and the integration will be from capital A to B. Okay, now, so remark. What is speciality for the blue one comparing to the red one? So blue one is well defined one-dimensional integral. It's rigorous, and therefore we make the following definition. So definition, first kind line integral. So how do you define it? Suppose you have curve, you have fxy, and you define this to be arc length. Okay, and more explicitly, you define this guy to be the integration from a to b fxt yt square root dx dt square plus dy dt square dt. And here, what is where C is a curve parameterized by x is xt, y is yt, with a bound from a to b. And I will talk about more about the bounds later, because that depends on how you choose the starting point and end point for C. Okay, and here you just one more word. This is arc length. So first integral is all about integration of some function with respect to the arc length. Okay, we can work out some examples to see this more clearly. Suppose you have a curve C. So where C is up half of the unit circle, x squared plus y squared equals 1. And the function is 2 plus x squared y. So the solution is okay. Now let's choose a parameterization. Choose step 1. We need to choose a parameterization when we do computation. And here, a very convenient way is cosine, sine, and you need to choose the angle. So here you see the angle will be between 0 and pi, and then you just put 0 pi here. I will tell you later that for first kind of integral, you can make your own choice of the starting point. So as soon as the bound is correct in this way, that means you can integrate from this side to this side. Okay. From this side to this side, or from this side to this side. The answer is the same, but only for first kind of line integral. Okay, second step, we just use the formula there in step 2. Let's call this integral I. So I is 0 to pi, and you plug in 2 cosine square sine theta. And then for the last one, what it is, dx d theta square plus dy d theta square d theta. And now we simplify a little bit. And for this one, you have sine theta square plus negative sine theta. Negative sine theta square plus cosine theta square d theta. So this is 0 to pi 2 plus cosine square sine square d theta. And you have 2 theta. You can find the antiderivative. And for this one, you have 2 theta. And for this one, you use train rule. So you have cosine cube negative 1/3. Okay, then you evaluate at pi and 0. So you plug in, you have 2 pi plus negative 1/3. So negative 1 cube minus 1 cube. So totally you have 2 pi plus 2/3. So that's a line integral. Okay, so just a remark. So let C prime be the inverse of the curve C. That means if you go from this to this, then the curve inverse C prime is go from the other side. So this is initial, this is ending, and then for the yellow one, this is initial, this is ending. Okay, and C prime F ds equals to I better use this notation. Negative C F ds. Okay, this is very crucial for first kind of line integral. You can take your own orientation in the notation we will explain later. Okay, and in 3D, we can generalize the formula. And we still flatten it. We need to make the line straight. Okay, and the function, just t substitution. And then the tricky part is how to figure out this one. But you know, this is arc length. So we have the arc length formula. Leave it to you. Recall the arc length formula for curve in 3D. Okay, how to compute it? We always write down as an integral. Actually, at that time, we already know how to do it, but without mention. Okay, and plus dy dt squared plus dz dt squared. And then dt. Okay, and here, of course, you need to specify what's the relation between T, C, and AB. So C is parameterized by x, xt, y, yt, z, zt. And A is from A to B. Similar. So by making this choice, we already decide, because you trace the curve from A to B in this order, then automatically gives you some direction where your curve flows. So from XA, YA, ZA to XB, YB, ZB. Okay. Now let's look at a 3D problem. Sine z. Y times sine z ds over c. So x is cosine t, y is sine t, z is t. T is between 0 and 2 pi. And then the solution, you take gamma prime. So what it is, we first need to compute ds. So ds just gamma prime dt. Okay. That's why we want to calculate gamma prime. So gamma prime t, so by definition, we know before, dx dt squared plus dy dt squared plus dz dt squared. So you have square root negative sine t squared plus cosine t squared plus 1 squared, so which is square root 2. And therefore ds is square root 2 dt. And then you plug in. So I should be integration from 0 to 2 pi dt, square root of 2 dt, that's ds, and y is sine t. Okay, so this is t, and the z is also sine t. Okay, then you need to use the triangle formula, so sine square. So you have 1 minus cosine 2t, square root 2, 0 to 2 pi dt. Okay, so you have 1 over square root 2 t minus sine 2t, 2 square t, 2 pi and 0. And notice that the second part since sine 2 sine 4 pi, sine 0 are both 0. You don't have that. And then you only have 2 pi over square root 2, which is square root 2 pi. Okay, next we turn to the second kind, the line integral, or the second kind. Recall, before we interpret the line integral as integration of some function with respect to the arc length. The reason why we do that is because here you only have some kind of dt here. You are integrating one-dimensional thing. But here, you might have some, for example, if your f to be capital F, so this guy cannot match up with dt because it's a three-dimensional thing. You cannot integrate a three-dimensional thing with respect to dt in the usual way. Okay, unless we do the following interpretation, unless ds is a vector. So if you have this idea, then you can carry out the second approach to define the line integral. So let's be more specified. Suppose you have this. So I change the notation to R, but also you can use S with arrow above. Okay, then as soon as you have dot product, there's no problem because here you will have scalar function, which is same as this one here, scalar function. Okay, now let's set up the coordinates and carry out the computation. So suppose f is p plus q into d for simplicity, and the gamma t is xt, yt is a curve in 2D, and t is between a and b. And then for this dot product, because we interpret this as a vector so that we can do true dot product. We write dr, this. Notice that we never define this guy. Okay, so this defined to be dx dy. Okay, then here you have p dx. Okay, so let's carry the variables at this moment, dx plus qxy dy. So this is a usual form you see in your textbook. Or in some real study, they call this as line integral over the second kind, and it seems like you have a lot of terms, but if you turn back, you can narrow it down to this form, which is quite similar to the previous one, but with a different interpretation. Okay, but basically, you cannot do any calculation based on the blue box at this moment. So we always flatten it. So how to flatten it? We will talk about a little bit later. But here I can give you the formula. You still do integration from a to b, and then f. So you just plug in all the data, x, t, y, t. And the dot product, you change dx to dx dt, dy dt, and then dt. Okay, therefore you have dt here. So this match up with one dimension. And for the whole thing inside, no matter how complicated it is, after the dot product, it's just a function of t. And someone would like to write in a more convenient form, f dot gamma prime t dt. Okay, and this is as fundamental as this formula here. Yeah. So basically, you can view the right-hand side as your definition. View it both as the rigorous definition and efficient way to compute. And when we do problems, we will make it clear. The key point here is parameterization. And similar, I would like to write again. So here, f dr over c can be written down as f, or you have p xt yt times q xt yt, this guy, dot gamma prime t. This is tangent vector. Okay, the whole thing you do dt. So the right hand side, both definition and the way to compute. And physical meaning, before we do actual computation, we introduce some physical meaning of the second kind. For the first kind, as I said, it's a kind of the total mass over some string with certain material. It's not equally distributed. Therefore, you have density function f. If it's equally distributed, then the total mass just a constant times the arc length. So arc length of a curve, we already know how to compute it. So basically, I can make a remark. basically we already know one very important example of line integral of first kind. So what it is, this is compute the arc length, the length of a curve. Okay, and if you write down in the current notation, you are just integrating the constant function 1 over curve S with respect to ds. Okay, then the physical, okay, now remark 2, physical meaning of the line integrals of the second kind. So suppose you have this one, and then this is a trajectory of a particle. Okay, and suppose here particle, and then you have some force field along this trajectory. For example, some electric field or the magnetic field. So this is F. But actually, this field not only on this line, it's on the whole space. Just because we care about the particle, we restrict ourselves to this line. If you choose different particles, then you have different values of F, X, Y, different X, Y. Okay, and then what is R prime? Recall this is a tangent vector. Okay, so you always do the dot product. Dot R prime. So when you do integration, so this actually is what it is. This is work done by the force field F along C. Okay, and probably I will stop here this moment. Next time we will do more examples.